Section 2.11, alkynes. We talked about alkenes. Alkenes are hydrocarbons with double bonds. Alkynes have triple bonds. So an alkyne is an acyclic, unsaturated hydrocarbon that has one or more carbon-carbon triple bonds. The functional group is that triple bond, and the naming of these is that we use the suffix -ine. Y-N-E. The general formula, CnH2n-2. From alkane to alkene to alkyne, we're removing two hydrogens. And the simplest alkynes are C2H2 and C3H4. So nomenclature. The nomenclature follows the same rules as for the alkenes, except we're using a different ending, alkyne. So if we look at this example over here, again, we're always looking for the longest carbon chain. This has a 4-carbon chain. For the ones with double and triple bonds, it has to include the multiple bond. So this is the longest chain that includes the triple bond, 4 carbons. So that comes from butane, and we change the ending to YNE. So this is butane. We're going to give a number here specifying where the triple bond starts. And the triple bond takes precedence over the other functional groups. This has a methyl group on it, but we need this triple bond to have the lowest number. So we're starting here, 1, 2, 3, and we've got a methyl group on the 3rd carbon. So this is 3-methyl 1-butane. This guy over here, again, we're looking at the longest chain that contains the triple bond. There's 7, so it comes from heptane. We change the ending to heptyne because there's a triple bond. And numbering, this way we get 1, 2, 3. If we numbered the other way, 1, 2, 3, 4, we get 4 on the first of the triple bond. And that would give us lower numbers for the methyl groups, but that's not important. The multiple bond comes first. So that one is 6,6-dimethyl 3-heptyne. Some compounds have more, pointing in the wrong place. Some compounds have more than one triple bond. So this is a diene. That's so hard to say. 7 carbons, so heptane. 1 triple bond would make it heptyne, but there's 2 triple bonds. So di is a prefix meaning 2. It's a heptadiene, and they are on the 1 and the 6 carbons. Any questions?
The formula you gave previously, is that for just one triple bond?
Yeah, the general formula that they're giving you is if there's only 1 triple bond. So the simplest alkyne is C2H2, and it has a special name. It's called acetylene. And you may have heard this word before. Welders use acetylene torches, and this is the compound that they're burning in there. So some of the simpler alkynes are named as acetylenes, and so this guy here has a common name of methyl acetylene. Here's that triple bond between those 2 carbons, and there's a methyl group on it. That's a common name. What would the IUPAC name be for that guy? 3 carbons with a triple bond. 3 carbons, mom eats pickled propane, right? Triple bond, so that would be propyne. And where would the triple bond be? Be on the carbon 1. So that would be 1-propyne. Then we also have to ask ourselves, could it be anywhere else than on the number 1 carbon? If we put it over here and made this the single bond, it would still be 1 propyne, wouldn't it? So in a situation like that, then we don't actually put the number because there's only one. Propyne can only have its bond in one place. So this is the IUPAC name, propyne, and this is the common name, methylacetylene. And this guy over here is commonly called dimethylacetylene. What would that be called under the IUPAC system? 2-butine. Because 4 carbons is butane, there's a triple bond, butine, and the triple bond is on the second carbon. So just be aware of those common names. They are not that important. Okay, isomerism in alkynes. We don't have any cis-trans isomers with alkynes like we did with the cyclic hydrocarbons, the cyclic alkanes, and with the alkenes, with the double bonds. The reason for that is we've got a linear bond there, and so there's just no possibility for isomers in terms of, you know, cis and trans types of isomers. So we can have skeletal isomers where the carbons are connected differently. Both of these isomers have 5 carbons, but they're connected differently. They each have a triple bond. And we can have positional isomers where the carbons are in the same arrangement. Here the carbons are linear, and here the carbons are linear, but the triple bond is in a different place. This guy looks kind of funny, actually, and this guy does too. There's a triple bond, and this is just straight. And that's because, and you can do this with the model kits that we have out right now. When you have a triple bond, you end up with a linear geometry around that carbon. Let's draw a picture. Actually, I think we can just look at like a Lewis type structure. So say we had something like this. Remember, carbons always have 4 bonds. So this carbon has a single bond to the hydrogen, and it's got a triple bond to this carbon. Vesper theory told us that we consider the groups of electrons. This single bond is one group of electrons, and the triple bond is one group of electrons. And they're going to get away from each other. Valence shell electron pair repulsion theory. They're repulsive to each other. There's 2 groups, they can get away by being on opposite sides. And so those are in a straight line. The geometry around this carbon is also in a straight line. The geometry around this carbon, it has 4 bonds. That's going to have a tetrahedral geometry. So the alkenes with the double bond had a trigonal planar geometry on those carbons, and the alkynes have a linear geometry. And when we draw these line structures, we draw them roughly how their angles are. And so here's a carbon right there, and there's a carbon in the middle, and there's a carbon here. We can tell there's a carbon here even though there's no angle because the triple bond only goes part way. If this was only one bond, then we would draw it a little differently. So there's a carbon here, and there's a carbon here, and there's a carbon here. If we meant to represent just 2 carbons, we'd have to do something like that. But we wouldn't make a bend here because it's not bent, it's straight. So hopefully that's not too confusing. So we can have isomers based on how they're connected and where the triple bond is. Physical properties are going to be very similar to those of the alkenes and the alkanes. They're generally insoluble in water, soluble in organic solvents. Their densities are less than water, and their boiling points increase with molecular mass. The low molecular mass alkynes, the smaller ones, are gases at room temperature. Then as they get bigger, they become liquids and eventually solids. chemical properties, that triple bond functional group behaves much like the double bond functional group in the alkenes, and so they undergo similar chemical reactions. Alkynes are flammable, and they also undergo the addition reactions that we talked about for the alkenes. The difference is that because it's a triple bond, you can actually add 2 molecules of the reactant instead of just 1. So in this example down here, we've got propyne with this triple bond, and if we do, what kind of reaction would this be adding hydrogen? Hydrogenation. It's a little unfortunate that halogen and hydrogen are real similar words. This is hydrogenation, and so the hydrogen can add across that functional group. So we can imagine it going like this. And I imagine, it's like a spaceship and it's coming down to land. And 1 hydrogen goes here and 1 hydrogen, wait, got ahead of myself. First it comes over here. Comes in and lands. 1 hydrogen here, 1 hydrogen there. What we get then is there's 2 hydrogens now on this carbon, and there's a hydrogen on this carbon when there wasn't previously. And that triple bond has become a double bond. And then that will undergo another addition reaction, and we'll end up with an alkane. Because the alkenes are reactive, just like the alkanes are, when you do have conditions for a hydrogenation reaction, it's very difficult to stop it here. It's hard to just add 1. And so you'll tend to just go all the way to the alkane. But it'll take 2 molecules instead of 1.